mean, I can start?
No, sir.
Fatima,
Yes, sir.
are you ready?
Yes, sir.
Anjit, you can share your screen.
So maybe Ashokan sir has to stop sharing.
Sir, could you please stop the share?
Yeah.
Honorable dignitaries and fellow members of the IEEE community, a very pleasant afternoon to all of you. It is indeed my privilege to welcome each and every one of you to the first keynote session of the 5th edition of IEEE RAICS 2020, an international conference organized by the IEEE Kerala Section on recent advancements in intelligent computational systems. I now invite Dr. Disha VR, who is the Technical Program Committee Co-Chair of RAICS 2020 and also the Chair of the Robotics and Automation Society of IEEE Kerala Section, to deliver the welcome address and introduce Dr. Asokan T, who is the keynote speaker for this session. Over to you, ma'am.
Thank you, Fatima. A very warm good afternoon and hearty welcome to the first keynote of IEEE RAICS 2020. So it's my pleasure to extend a warm welcome to the keynote speaker, Dr. Asokan T, Head of the Department of Engineering Design, IIT Madras, on behalf of the organizing committee and everyone present here. Thank you, sir, for joining us for this keynote session in spite of the busy schedule. So warm welcome to all the organizing committee members of IEEE RAICS 2020, Satish Babu sir, Vijana ma'am, Bobby, Philip, Nandan, Professor Nandan, Dr. Jason, Dr. Suresh K, and Professor Shankar to this session. So special welcome to all the EXICOM members of IEEE Kerala section present here and all the paper presenters. I also extend a hearty welcome to all who are working hard behind the scenes for making this event happen. Now, moving on to the introduction of the speaker, Dr. Asokan T received his PhD in mechanical engineering from IIT Madras in the area of electro-hydraulic controls for robotic applications. He then spent 6 years as a researcher at Robotics Research Center, Nanyang Technological University, Singapore, working in the area of mechatronic systems and robotics. He was instrumental in developing the remotely operated underwater vehicle and a 7-axis underwater manipulator at NTU Singapore. Prior to this, he spent 3 years in DRDO as a scientist. He joined IIT Madras in 2006 and was awarded the Stanford India Biodesign Fellowship by Stanford University in 2009. He has completed postdoctoral fellowship at Stanford University as well. Dr. Asokan T is also visiting fellow at University of New South Wales, Australia. He's currently the National Secretary of the Robotics Society as well. Dr. Asokan has published more than 120 papers in international journals and conferences and has filed 20 patents in India, USA, and Singapore. He is actively involved in many sponsored research projects with an approximate budget of rupees 500 lakhs. Now I am handing over the mic to Asokan sir. Thank you.
Okay, good afternoon, everyone. Thank you very much for attending this session, and thanks to the organizing committee for giving me this opportunity to present my work to the IEEE society and the participants of this conference. So I'll be talking about the design and control of autonomous robots for field and service application. As you know, it's a very vast field. So I'll be just giving you a brief intro to the challenges in making autonomous robots and what are the issues that actually still we consider it as a challenge for developing fully autonomous robots. So before getting into the topic, let me briefly tell you what I do as part of my teaching and research. So as introduced, I am in the Department of Engineering Design. So my primary interest is in robotics. Of course, I work in the other areas like medical devices and other design projects also. But primarily, I look at the problem from three perspectives. One is the design of robotic systems. So how can we design innovative robots or innovative robotic systems for field or service application? And once you design a robotic system with some novelty, we need to look at the dynamics of the system to ensure that the robot will perform the way you want. And if you want to do that, we need to develop the mathematical models, then simulate it, and then try to see how the open loop performance of the system is. And then we need to go for the design of controllers or the control system to ensure that the system behaves the way we want. So this is basically the three areas I focus. And most of the robotics projects which I do primarily focus on these three aspects. So any robotic application which has got these three components will be of interest to me. So I've been working on various projects for the last 20 years. I started my research with underwater robotics and now currently focusing on medical robotics, or how do we develop robotic systems for medical applications. But today's talk will be primarily on autonomous robots, or what are the difficulties in developing autonomous robots. So we talk a lot about autonomy, and as you know, people are talking about autonomous robots, humanoids, and self-driverless cars for many years. And we see that still we are far away from having a fully autonomous robot. And a person who is not fully into robotics will think, oh, what is the challenge, or why the people are not able to come with autonomous robots? Because you see many things in movies, and many times we believe that these things are really possible, and why it is not coming into the market, we used to wonder. There are many challenges in developing autonomous robots. I'll just touch upon few of the things, few of such issues, and then briefly explain a project which we did on development of autonomous underwater robots. That's going to be the agenda. So I have only some 35 minutes left, so I'll try to finish it as within the time. So I'll be talking, starting with autonomy for robots, basically talk about the different types of robots and where we actually use these kind of robots. If you look at the history of robots or the evolution of robots, you will see that we had industrial robots somewhere in 1960s, and till 2000 we were having only industrial robots, and most of the other robots were still in the laboratories. It was only in 2000s everyone realized that we have developed too much of technologies, or we have too many systems and technologies available, which need to come out of the industry and then come out of the shop floor and then move to the home or to the places where actually human will be interacting with the robots, or where the robots can be of much use to the human. That is where we started getting this underwater robots, medical robots, and personal robots, and you name any field, we can see that there are some applications of robotic technology in that field. And that is one of the important aspect of robotic research also, because the current research and development in robotics is primarily propelled by the application field. So if you have an application, if you can develop a robot for an application, that is basically the contribution that you can make. Parallelly, we'll be developing control systems and navigation systems and other things. But primarily, when it actually go to the field or come to an application, that is where actually we are making a real contribution. Now coming to the these are actually some of the robots which actually we call it as the field and service robots. So what you are seeing is an underwater robot on the top, and then you can see that the mobile robots, and of course this is an industrial robot which is familiar to many of you, which has got a fixed base, and all other robots what you are seeing are having mobility. So the requirement in an industrial robot is completely different from a field or service robot, because you add many things to the robot and it's more complex. And as you can see here in the last video, the bottom corner, the humanoid robot. And if you look at that, is maybe the first of the complex out of all these robots, because of its two-leg locomotion, working locomotion, and then the requirement of having different joints and different. So it's very possible to develop your humanoid robot, but the challenge is that how can we make it close to the human and it is to the scale of human application. So whatever we have at present is more like laboratory purpose, with very limited application for practical use. You might have seen, you have heard about robots like human-like robots, where the walking computers and they have beyond these are relatively similar to make, but the robot is much more complex. Now, these are the different kinds of field robots available. Now, the question is that when do we call this as an autonomous robot, or how do we actually classify them into different categories? And you look at the level of autonomy provided in the robots, we'll be able to classify them into two major classes. One is the remote operation, the other one is the autonomous operation. And the remote operation, as the name suggests, the robots will be controlled by an operator from a remote location. And things are not that difficult in this case, because the control is still with the human, and all the decision making is carried out by the human, so it can do many complex tasks. But if you look at the other end, an autonomous robot, there is no human control, and therefore the robot has to make all its decisions and execute the decision like a human can do, or a person who with a little bit of autonomy or some level of autonomy. All the tasks which that person can do, the same the robot also should be able to do. Unfortunately, we are still very low on in this category, autonomous robots, and because of that, we cannot do any complex tasks with autonomous robots, or very limited tasks only can be carried out by the autonomous robots. So the challenge now is to see how can we bring up this autonomous robot to the level of task complexity that is of a remote operation. And then we can say that, okay, we have achieved some kind of autonomous operation for the robot. Otherwise, the current autonomous robots are, with few exceptions, most of them are like, you can have some kind of camera and then do some kind of observation. And beyond that, doing any task is very challenging for an autonomous robot. But why is this so? Because we know that we have the algorithms, we have navigation algorithms, we have control systems, we have sensors, and with all these things, why is it not possible for us to develop fully autonomous robots? So that is one question most of the people will ask: why can't we do this? Or what are the challenges in making these robots? Okay, so before going to the autonomy, just talk about one or two slides on the remote operation. So the remote operation is normally called as a tele-operation, where we have two parts for this tele-robotics. One is known as tele-operation, the other one is tele-presence. So for any tele-robotic application, we need to have two aspects. One, that you should be able to operate the robot from a remote location. That means you need to send the control signals to the robot from your place of wherever you are sitting. And the other part is that you need to get the feedback from the robot, and then you need to create an environment where you feel that you are actually at the place where the robot is. So that is basically known as telepresence. So telepresence is achieved through various kinds of feedbacks. You can get a visual feedback through camera systems, or you can get a touch feedback through haptic system, or you can get a sound feedback. So if you can create the same environment as where the robot is, then we call it as a telepresence system. So this is just come to a good level of development and implementation. One of the most important development in this area is the surgical robots. So most of you must have heard about surgical robotic system. So there are robots which can actually do surgery, and they go for the tele-robotic principles. So you will be having a master robots. Let me open this. Sorry. Yeah, so you can see that the doctor will be comfortably sitting at a remote location, where it's called this surgeon console, and he will be operating a master robots. The master robot will be controlled by the surgeon, and at a remote location, you will be having slave manipulators, and the slave manipulators will be having the surgical tools. And depending on the commands that the doctor is giving, the slave robot is able to do the surgery. And then, of course, you'll be getting the telepresence to some extent by visual feedback as well as the force feedback and touch feedback from the surgical site through the slave robots. So this is a typical application of tele-robotics, or the remote operation of a robot from by an operator sitting at a faraway place. And the complexity here, though challenges are there in developing it, we have most of the technologies are available, and that's why we have good surgical robots available in the market. Many hospitals are having surgical robots. Even in India, we have more than 10 such robots in different hospitals. So we have actually worked on such a robot design. I don't have time to go through the details, but I'll just show you a video of this robot what we developed as a surgical robots. So this is it has got a master and the slave manipulation. So this is the master robot, which is actually a 6 degree of freedom manipulator with additional degree on the grasper. And there will be two such master robots, and these two master robots will be operated by the surgeon, and then this will be connected to the slave robots. So this actually shows the slave system. The slave system also will be having the same number of degrees of freedom, and this is the tool which actually will go into the surgical site where the surgery will be carried out. And then you will be able to map this to the master operation. So you can see this person is actually controlling the master robots, and then he's by controlling the master robot, he is able to manipulate the slave robot at the remote site, and he'll get the feedback from the visual feedback, and the tactile feedback can be, or touch feedback can be obtained through the sensors. So that is basically the tele-surgical robotic system. So just wanted to tell you that it was the initial, I mean, that is how the robots moved from completely from the industrial field to the surgical field. And now, if you want to make, so we know that it's still controlled by the doctor. So the robot as such has no intelligence in this case. The robot is still following the instruction from the master robots. Now, as we move to the next thing, that is the autonomous robots. So the logical development is now, how can we make this robot intelligent so that you don't need to have an operator sitting at a remote location and controlling the robots. So that is basically autonomous robots. And most of you heard about autonomous cars. That is one of the latest craze in the robotics field. How can you make cars or other automobiles fully driverless, where we can build intelligence into the system and then do it. So you might have heard about the Google car and other autonomous cars developed by various agencies, various research centers. So this actually shows one of the such videos of testing of an autonomous car. So as you can see here, the car will not be having a driver. The car has been programmed to go through different paths and identify its own track, then avoid obstacles, identify traffic signals, identify pedestrians, follow the traffic instructions. So all these things are being programmed to the robot, and the robot has to follow the instructions and take decision based on the sensor input, the sensor data, and continue the task and finish it and go and park or whatever the instructions given to the car. So all this need to happen without any intervention from the operator or any external command signal going into the robot controller. So how can we do this, or what are the basic requirements in order to achieve this task? So this is what actually as robotic scientists we are interested in. Now, let us see what are the basic requirements for any autonomous robots. If you look at the autonomous robots or any robot system which need to behave with its own autonomy, there are few fundamental requirements to be satisfied. So this is, I mean, for any such autonomous robot, whether it is an autonomous car or any other robot, whether it is an underwater robot or an aerial robot, the robot should be capable of doing a few things without any intervention. So first thing is basically the robot has to answer these questions, the 3 questions that a robot need to answer. So the first question is, where am I? So what is the position of the robot in its environment, wherever it is? So it can be a ground, it can be a room, or it can be some other place. So the robot should be able to know where is it or what is the current position of the robot. So it's like a human also. When we are in a very unknown place and we have been asked to do something, first thing we need to try to understand is, or try to identify is, where am I now? And then once you know where you are and when you know where you are going, then you need to plan, oh, how can I reach there? So if the robot can actually answer these questions and execute its answers, then it becomes an autonomous robot. And to do this, we need to have a few things embedded into the robots. That is, the robot need to have a model of its environment. I mean, the robot should know to decide where it is. It should know what are the possible locations or what are the which place it is. So there should be a kind of a map given to the robots, or a digital map should be provided to the robots. And if it is not there, then the robot should be able to make a map of its own. So this is basically the first requirement in order to answer the question, where am I? And once it has a map, and within the map, the robot should be able to perceive its environment. So it should be able to look around and then see what are the things that the robot can see, and then based on the information, it should be able to analyze the environment and find its position within that environment. So that is the first requirement to answer the question, where am I? So the robot has to have a map. It needs to have enough sensors to identify the surroundings and analyze the surroundings, and then identify its location within that environment. So that will answer the question, where am I? And then the next question is, where am I going? How do I get there? So it has to plan. So once it knows its location and where it has to go, it has to do a planning. We call it as path planning or trajectory planning. And once it is planned, it has to execute that motion. So it has to start moving from one point to the next point, and through all the via points, it has to reach its location. And as it goes through this, it has to identify the obstacles, avoid the obstacles, and ensure that the robot is safe, and many things it has to do. And once we make this robot to capable of doing all these tasks, if we can actually make the robot to do this, then we can call it as an autonomous robot, which can actually be deployed for any field or service application. And we call this the locomotion and navigation of a robot. So we need to deal with this locomotion and navigation in order to execute its motion to the target. So the 4 important elements involved in all these activities are the perception, localization, planning, and motion generation. So the perception is basically how do you perceive the environment. Localization is how do you identify the location of the current location. Planning is how do we actually execute the task assigned to it, and then finally executing the task, the motion generation. So if the robot is capable of doing all this autonomously, then it has got the full autonomy to carry out the task. So as you can see in this slide, so the robot is in the real world environment. So you can see it is in the real world environment, and continuously it will be having its perception. So through sensors, it will perceive the environment and create a model, and then localize itself. And then once it is localized, again based on the information and the algorithm, it will do a cognition, basically taking decisions, what it has to do, how it has to do, and where it has to go, all those decisions to be made, and then get a path for travel, and then do a motion control, and then move. So this will be continuously operating on the autonomous robots. And this is the primary requirement for the robot to be autonomous. So you may wonder, okay, what is the challenge? So we have sensors to do the perception. We have a lot of algorithm for localization. We have a lot of algorithm for cognition. And we have motors, actuators, and control algorithms to do this. So why are we not able to do this and make fully autonomous robots? Yes, we have a lot of technologies available. We have a lot of sensors and other algorithms available, but everything comes with its own limitations. So there is nothing which actually comes without a challenge. And all these challenges, when you try to overcome all these challenges, then you find that it is not that easy to develop the fully autonomous robots. So what are the challenges? The challenges will be coming in the, okay, so this is where actually in an implementation of the autonomy, the four elements of perception, localization, and navigation and motion execution will be actually implemented in 3 blocks of in an autonomous robot. We call it as control, guidance, and navigation. So this control, guidance, and navigation will be able to answer the question, where am I going? How do I get there? So that is basically the requirement in the robot. So every robot comes with its own control, guidance, and navigation system. And this actually poses a lot of challenges in implementing and getting the robot moving from one point to the another point. And if you see many of the autonomous robots which you develop in the lab or for some application, you will see that they are extremely slow. They are not at the speed at which you want them to go, because they need to do a lot of processing of information in order to move from one point to the other point. Most of the time we do many things without even knowing that we are doing a computation inside our brain. But that actually comes from our experience, our own experiences and our own understanding. But the robots don't have that kind of an experience, so everything has to be computed and it has to be executed. Okay, so as I told you, the first part is the perception. So the sensors and the sensors uncertainty are the main challenges in perception part. So as I told you, every step has got its own challenges. So the sensors is the first part, which actually give the perception of environment. And you know, there are multiple sensors available for autonomous robots. There are position sensors, velocity sensors, and obstacle sensors. And we should be able to use all these sensors to get a good perception of the environment. But what actually happens is that all these sensors comes with its own uncertainty. No sensor is 100% correct. If you use a sensor to measure the distance from one point to the other point, if you use a laser sensor or a sound-based sonar sensor, you will see that if you make 5 measurements, you will get 5 readings. They may be very close to each other, but they will be having a 5 readings. So you cannot really use all the 5 readings to do this. So we know that there will be an error in always when you do the measurements. And when you do this measurement at different times or different temperatures or different humidity, again, you will see that there are variations in the readings. So the question is that how can we actually have a good estimate of the reading without any uncertainty? And that is not possible. So we need to always consider the uncertainty in the sensors. And then the features available in the environment that also will be having many challenges, because a door and a cupboard will look similar in a camera image. So how do the robot will distinguish between these two? A cutout of a human and or a real human may appear almost same as in the image for a robot. So how the robot can actually make a decision whether it is a real human or just a 2D cutout. So these are the challenges that in terms of sensors. And this sensor uncertainty, of course, it is being addressed through various means. So one of the approach is to basically look at this as a probabilistic model, and probabilistic robotics has got a lot of algorithms and a lot of methodologies to model this uncertainty and then see how this uncertainty can be used in order to predict the position of the robot, or how the robot position can be predicted even under the uncertainty. So that is one challenge that is being addressed. So this is again a part of the probabilistic robotics law. So there is something called an error propagation law. That is, if you use the distance from one point to another point as to locate the position of the robot, then if there is an error in the distance, your position also got an error. So how much is the error that is propagated to the robot position is basically addressed through something called an error propagation law. So this error propagation law plays a major role in estimating the position of the robots. And if the sensor has got an error, that will propagate to the position of the robot, and then whatever the robot do based on this position will also having an error. So after some time, if the robot starts moving based on this information, after some time you will see that the estimate of the position is completely wrong, or there is a large uncertainty in the position of the robot itself, and that is where the robot loses its control, and then you will not be able to get any autonomous operation from the robot. So this is one challenge we still have, and though there are many algorithms, we still have a lot of uncertainties in this. To some extent, these are solved for outdoor robots through GPS and other methods, but for indoor robots, positioning is still a major challenge because of the sensor uncertainty. And people use multi-sensor data fusion to overcome this challenge. Also, you can use different sensors and then fuse the data and then try to reduce the error. So what will happen, you can reduce the error, but then your computation increases, the robot becomes much slower compared to what you are expecting it to have. Okay, so if you are just looking at the localization part, you can see that how the robots actually do this. So it will actually use its encoders on the wheels, and then see how much it has traveled from a known position, and then calculate where it has reached based on the odometry that the sensor attached to the wheels. So if it's running at a particular RPM for a period of time, then it is possible to predict how much the robot has traveled and where its position is. But then, as I told you, the encoder will be having errors, so you need to correct the error. So what we do is basically to use something called camera-based imaging system or some other kind of matching, and you observe using sensors and then correct the error using this sensor. So this is basically the probability-based localization method, where you use multiple sensors and then use the matching algorithms to predict the position of the robots. So that is just one of the methods for localization, and there are many other methods to do the localization of the robots. Okay, so to explain this probabilistic map-based localization in a better way, so I can just using this picture. So assume that it's a 2D environment. The robot is moving in a straight line, and it is starting from a completely unknown position. The robot does not know where it is currently, so it assumes that it could be anywhere in the environment. So it says that okay, it has a 100-meter travel, and it does not know whether it is at 20 meters or 30 meters or 50 meters. So it assumes that okay, I could be anywhere in this environment, so have an equal probability for all the locations. So that is that the shaded line shows that equal probability for the robot to be anywhere in this location. So that is where the robot will start. And the robot has been given a map saying that there are 3 poles or 3 posts on the path, and the location of these posts are already given to the robot, saying that okay, the distance between these posts are so and so. So that is the information the robot has. Now the robot starts moving, and it sees the first post over here, and then the robot knows that okay, it could be either at this location, or this location. So because the robot knows the map, so it actually says that it could be anywhere in the location. Now the robot starts moving again, and there is nothing to see, or the robot is not able to see anything. So its uncertainty again increases. As you can see, the uncertainty changes over here. So the probability was very high here, but it has gone down here again. The probability has gone down. Now the robot starts moving again, and then it sees the second one. And once it sees the second one after traveling a particular distance, it knows that it is definitely at this point. It is definitely at this point because there is no other point where actually the robot will be able to see 2 posts so close by, and therefore its position is at this location. So that is the way how the probabilistic map-based localization works. So if you have a robot moving in a known environment, and you are given the map, then the robot has to do this continuously, check for this data and analyze it, and then only it will be able to predict its position. And whenever the position is not known, and all other calculation what the robot does based on the position will be going wrong. So these are the challenges in having a indoor locomotion for the robot as it has to do the localization. Okay, let me skip this and then, okay, so this can actually be done through autonomous map building. So I'll just skip this part. because if the map is not there, the robot will be able to create its own map and then do the mapping. So let me skip this part and let me go to the main building blocks if you want to really develop a fully autonomous robot. So as I mentioned to you, so you have this navigation system, then dynamics and the controls, guidance and control system. So you need to develop these two, the navigation system and the vehicle guidance and control system, in order to develop a fully autonomous robot. So what I mentioned was only a one of the challenge. There are many, every stage you will be having this kind of challenges. Localization just mentioned, but in the guidance and control also you will see there are so many other challenges. So there are many path planning algorithms. Okay, so in order to do the guidance and navigation, you need to have path planning algorithms, and you need to have obstacle avoidance algorithms. There are multiple path planning and obstacle avoidance algorithms existing in the current literature, but each one comes with its own difficulties. There are no, none of them will be universally acceptable. Some of them will be good for some environment, some of them will be good for some other environment. So we need to have a good path planning and obstacle avoidance algorithm in order to give full autonomy for the robots. So let me skip this and then let's go to the implementation part. So I have only another 5-6 minutes. So let me explain to you how we actually implement a fully autonomy for a field robot. So I'll take the example of an underwater robot. So this is the okay, this is the general description of an autonomous underwater vehicle. The vehicle will be fully autonomous. That means you don't need to have any human control for the robot. So the robot will be propelled using these thrusters and control planes for control forces. And then there will be collision avoidance sensors and navigation systems and other things inside the robots. So the robot will be able to move from one point to another point without any human intervention. So it has to do all the path planning, obstacle avoidance, navigation, and control by its own. And in general, the design of such robots will be having a hull in order to overcome the water pressure. And then all the electronics and other things will be inside the hull, and you will be having the thrusters and then these control planes in order to generate the control forces. And as you can see, there will be many things inside. So its navigation system, power supply, payload, and control guidance system, everything will be inside this, so that there is no contact with the water for these items inside. And this has to withstand the pressure, water pressure. Otherwise, it will actually break, and then the robot will be lost. You can have different shapes for the robot. It can be a flat fish or it can be a torpedo shape. So depending on the requirement, you can choose this kind of a shape or a shape of this one. So as I mentioned, the hull need to be waterproof. It has to withstand the hydrostatic pressure, and the drag forces should be minimum, because as it moves in the water, there will be a lot of forces acting on it. And we have to reduce the drag forces, and then the controllability and maneuverability is an issue. So depending on that, you need to modify the shape so that it will be easy to control and maneuver. And then there will be thrusters and control planes attached to the robot. So you can see this is a flat fish shape one. Will be having thrusters, and horizontal thrusters and vertical thrusters will be there, so that it can go up and down and move forward also. These are some of the design features. I just wanted to tell you that many of these systems are available off the shelf, so you can actually buy it and then develop autonomous robots. And develop a physical robot can be developed without much of a difficulty. Okay, so and then there are multiple sensors available. So you need to have navigation sensors, health monitoring sensors, and control sensors, and of course the payload sensors also. Okay, so once you have this design completed, then you need to look at the dynamics of the robots. So you want to find out whether the robot will really move forward if you actuate the thrusters, and if you actuated thrusters, in what way it will move. So in order to study this, you need to develop the mathematical models. So there are standard methods for developing such mathematical models. And once you have the model, and if you know the parameters like its inertia and other parameters, you will be able to simulate the behavior and find out what way the robot will behave once we actuate the thrusters or the control planes. So that is one basic requirement in order to develop the autonomous robots. Or any robot, you need to analyze its dynamics and then study the behavior. And then you need to implement the guidance and navigation system to the robot. So that was more of a physical robot. Now you need to bring the brain of the robot into it, and that actually is the guidance, navigation, and control system. So the guidance system will take care of the obstacle avoidance and path planning, and the navigation system will ensure that the robot is moving along the required path. And this control system will take all this information and then decide which of the thrusters need to be activated, or which thrusters to be control plane to be activated, so that the robot moves along the desired path. So that is basically the implementation part, from where you can implement the navigation and guidance system onto the robots. And in the control algorithm and the guidance algorithm, you have many things required. One is basically the path planning algorithms. So how do we actually have a path from point A to B? What kind of a path can be designed? And then how do we actually avoid the obstacles when it is, as it is moving? If there is an obstacle, how the obstacle can be avoided. So there are many systems or many algorithms available for guidance system. So you have the waypoint guidance and obstacle avoidance requirement. So these are some of the algorithms we developed as part of our research. So this is known as a line of sight, improved line of sight method for path planning. So the robot has to move, if it has to move from start point to the goal point with these waypoints, the robot has to move along this path so that it just go over the waypoint and then reach the goal point. So this needs to be planned as a with an algorithm. And then you need to have the obstacle avoidance methods. So there are multiple methods like potential field method and other methods. So we need to have this kind of algorithms in order to have obstacle avoidance. So again, these are some of the research we did. We developed a new method called the multi-point potential field method for obstacle avoidance of underwater robots. And then with all this, we'll do the simulation studies to see how the robot will behave under various situations, path planning and obstacle avoidance. And once it is, once you are comfortable with all these, then in the C for the next trial. So this is actually an implementation. So with that, let me stop my presentation. I think I have taken slightly more than what was allotted to me. So thank you very much for listening. It was a bit, I think, fast. I had to continue, complete it in 45 minutes. So thank you very much for listening. And if you have any questions, I'll be happy to answer. Thank you.
If you have any questions, please post it in the chat box. Sir, I guess there are no questions. We'll move on. Thank you, sir, for those enlightening words.
I think there is a question.
So there's a question. What are testing procedures?
Testing procedures for what? I mean, because there will be multiple testing procedures. So you need to test the individual actuators, controllers, and control plane. And then you need to test the...
So for underwater UV.
Yeah, so the first thing is basically you test the subsystems like actuators. So whether you are able to get the actuation of the control plane within that time required. So if there's a large response time, then you won't be able to use it. So first testing is basically the subsystem level testing, and then I mean you have to do for all these, and then you integrate it, and then you do the testing for basically the flotation test, whether they are having a proper CG/CB adjustment, and then the what you call buoyancy and the buoyancy control. So you need to have either to have a neutrally buoyant condition or a positive or negative buoyant. So these are basically the static tests you do, and then you go for the water test, and then see whether you are able to get the desired speed or desired turning rate. So like that you do multiple tests, and then finally the test is more like whether it can actually go through the desired path or how much path error the robot is having. So these are the various tests that you need to do.
Thank you, sir. Are there any more questions? I guess that's all, sir. So thank you, sir, for those enlightening words. I now call upon Dr. Abhilash T. Vijayan, who is an assistant professor in the Department of Electrical Engineering at RIT Kottayam, and also a co-chair of Robotics Automation and Control track of IEEE RAICS 2020. Over to you, sir. Sir, you're on mute.
Sorry. Good afternoon, dear all. This is the second day of RAICS 2020. IEEE Recent Advances in Intelligent Computational Systems 2020 is a great initiative by IEEE Kerala chapter, a virtual conference responding to the need of the hour. We have just completed a nice and informative keynote address, Design and Control of Autonomous Robots for Field and Service Applications by T. Asokan, a pioneer and expert in the field of mechatronic systems. Let me move on with my duty by extending the vote of thanks to our beloved speaker. Okay. Dr. Jishamam had introduced her to the audience, but let me tell, we are really fortunate to have such an eminent person with 20 patents and more than 120 international publications as our keynote speaker. On behalf of the organizing committee and all the audience, let me thank you, sir, for your presence and the keynote address. This event, IEEE RAICS 2020, the 5th Biennial Technical Conference of IEEE Kerala Section, is the outcome of a great teamwork. The committee members, Engineer Satish Babu, Dr. Bijuna K, Dr. Bobby Philip, Professor Nandan, Dr. Jason, Dr. Suresh K, Professor Shankar, and Dr. Jisha. I take this opportunity to thank them all. Let me also thank all the executive committee members of the IEEE Kerala section and all those who are helping the committee in organizing the event. And there's no conference without participation, and I thank all the paper presenters for their contributions to this event. I hope I have thanked everybody who are behind this conference. Thank you all.
Thank you.
Thank you, sir.
And can I leave?
Yes, sir. We at IEEE Kerala Section would now like to present Dr. Asokan T, Head of Department Engineering Design, IIT Madras, with a memento as a token of gratitude.
Operation.
I would like to express my heartfelt gratitude towards everyone who has joined us here today. I would also like to thank the enthusiastic team of IEEE volunteers for their dynamic efforts and all the honorable dignitaries who have graced this occasion with their presence. Thank you for your support of our shared mission to advance technology for humanity. And with this, we mark the end of the first keynote session of IEEE RAICS 2020. We will begin the paper presentations of IEEE RAICS in the corresponding Zoom link at 3 p.m. today. And therefore, I request all the registered participants to join the same. Thank you once again.
Thank you. I'll leave now.
Yeah,
Yes, sir.
thank you, sir.
Thank you very much, sir.